well as at Sparrius Systems Engineering and Management. He provides training on systems engineering, project management, integrated logistics support, engineering management to people from the high-tech industry, and he's a fellow of the International Council of Systems Engineering in COSI. And as far as I understand, Ad was one of the founding members of COSI in South Africa, and he's been pushing it for a number of years now. So Ad, if you're ready to present, please, can you proceed? Ad, are you ready? Have we lost him? Sarel, is Ad ready?
They must just unmute also. Andries, I see Ad has mailed me his presentation, so if all else fails, I can present from my side if required.
I think let's do that. Ad, are you okay with that?
I think maybe he must leave the meeting and come back in.
Or he must just unmute. I can see he's muted. Okay. Sarel, we can see a blank screen.
Mute. Say.
There you go.
Okay, nou kan jy gaan. Hoe kan ek dit bly? Is jou rekening? Ja. Can I just check, can everybody hear me and can everybody see that screen?
Yes, but just mute the other computer. You got your feedback now.
Yeah.
But we can hear you and we can see a blank screen.
What do you see now?
Blank screen. Yeah, white screen.
Let's see it nog iets daar. So let's see it nog. So. Okay, so deze was een PowerPoint. Dit is scherm geshare. En hoe moet je dan net uitgekomen? Dat blijft je vraag. Om het knopje te drukken. Maar dat is nog niet scherm. Maar kijk net hier zo. Kijk hier zo.
Ja, Sarel and Ad, we're still seeing a blank screen. So just confirm when you share an application, don't share a screen, because otherwise it gives us, you know, whatever's on that screen, and it seems to be sharing a blank screen with us and not a presentation.
Okay, just hang on. Let's just see here. Share. Sharing is paused. So share. Is het met jou wat jy? Daai skerm. Give control.
Don't touch give control or anything. Just share your screen.
Now we share. It says presenting at the moment.
It's not coming through. It's basically just showing. It's not showing a screen.
If Rudolf can maybe just try.
Ja, dit kom misschien in PowerPoint. Die Rudolf. Okay, Rudolf. Ons kyk.
Okay, I will share.
Ek het stop sharing.
Perfect.
Ek het 'n skerm sien. Okay, daar is jou skerm. Rudolf, as jy nou is jy PowerPoint?
Yes, PowerPoint is displaying a slideshow,
I see it.
and yeah.
Lost is younger. Oh, yeah.
Okay.
Good. Ladies and gentlemen, good morning. As systems engineers are having a problem this morning, which goes all to the benefit of system dynamics. The topic of this morning is what's the difference between system dynamics and system engineering? They sound so much alike. Where is the one used? Where the other? Do they overlap? Next, please. Next, please. Yeah. So, at heart, system engineering is the engineering of man-made systems, complex, difficult systems. Systems engineering is not a job description. It is an engineering process that can be used by any engineer and any other people who aren't engineers. The system engineering process has, in fact, been based upon software engineering. What the software engineers did about 10, 15 years ago, what they were exploring, the system engineers are doing the same thing today on the same topic. We've learned a lot from them, and we are going ahead. Volgende alsjeblieft. Very simple definition. M is a model of S if M can be used to answer questions about S. That's a very simple model, very powerful one. And I'm sure you've seen this one before. All models are wrong, but some are useful. En ek is ook maar bly my van is nie boks nie. Here is an example of a model of a system. Can you just press the first button? This is not quite correct, but it should help. Ooh. So there's the system of interest. The detective people always talk about persons of interest. We talk about systems of interest. You see the boundary. There's the boundary which tells you where the world stops and where the system starts. It's an external system in the environment outside the boundary with an external interface, which is called number 3. Then there is an element. There's element number 1. There's element number 2. There's element number 3. There's an internal interface from number 3 to number 1. And it also shows you the last one, an interconnection between element 1 and element 2. This interconnection creates an interaction which hopefully provides constructive synergy, which gives us the emergent properties, which is the reason we want the system in the first instance. So this is a good model of a system, 3 elements with their interfaces, external system. Next one, please. So what kind of elements do we have? The first one is hardware, equipment, or software. And then we also use people, for example, operators or maintainers or mechanics, what have you. If you need people, you also need in turn support equipment, protective clothing if this is dangerous, documented procedures and perhaps certification of knowledge, training, a link to that, and facilities such as air runways for aircraft and dry docks for submarines and workshops, what have you. Those are the types of elements. I just showed you 1, 2, and 3. It can be any or more of these. Next, please. Now, we're going to be talking about the systems engineering process. How do we get that model of a system? And this process can be summarized as follows. The first step is determine the root business problem. Identify all the stakeholders and elicit and define all stakeholder requirements. Note root business problem, not a technical problem, a business problem. Then identify, define, and model alternative solutions and select the most appropriate solution. Note, there's a very clean distinction between the problem domain in the stakeholders and the solution domain. And you don't want, whilst you're busy with identifying the root problem, we are agnostic as to which particular solution, if any, we're going to use. That is the second bullet here, where we define and identify the most appropriate solution. Given that, of course, the solution is called the system. Determine the requirements for the solution system. Next one, please. We translate the system requirements to system functions. If you were clever, you would have written the requirements as functions. Next. Define all the performance requirements for each function and the verification requirements. For instance, we're talking about an aircraft. The main function of the aircraft is to fly. If it doesn't fly, it ain't an aircraft. Now, the question, that's the function, fly. Question is, at what altitude? At what Mach number? What speed? What is the duration of the flight? Those are all performance requirements which elaborate and actually define that function. And of course, verification is finding out that we actually achieve it. Will we be going to achieve it? Functions and their performance requirements, as discussed, will be implemented by the system of interest, the solution. Next, please. Then we develop, there's something missing here, just continue. Yeah, there it is. Develop all sub-functions for each function. So we take a function break and we break it up into sub-functions. Jointly, those sub-functions will make up the function. Then develop all performance requirements for that sub-function with the verification requirements. And once we've got that, now is the design problem. What is going to implement each of these sub-functions? The sub-functions and their performance requirements will be implemented by those elements in the system, as we saw just now, number 1, 2, and 3. So that's essentially the process. And when we talk about this process, it is deeply influenced by a large number of models. Next, please. A system engineer, all system engineering uses models. And we probably start off with mental models in our heads, stuff that we think of. They will have to transform into semantic models, narrative, a description. And then even later we get specifications and drawings and formal documents. And that is what system engineering was for a very long time, a document-centric modeling. Prototypes, very important, be they scaled down prototypes or full scale. And then, of course, the operating manuals, maintenance manuals, repair manuals, other technical manuals, they are also part of the models used later on after production for operations and support of the system for us. Next, please, Rudolf. So, there are 3 categories of models which are rather important and fundamental in this discussion. We have descriptive models, which describe and analyze a problem or deepen understanding in an existing problem. They are descriptive. Then we have prescriptive models, which specify the behavior, the functionality, the performance, the structure of some system. Now, to my way of thinking, system dynamics is mainly concerned with descriptive models, describing and analyzing a problem. How will this pandemic actually progress? If we increase the price of petrol by so much, what will the impact on the economy and the number of employment be? Prescriptive model, on the other hand, are when we engineer man-made systems. We build aircraft, we build chemical process plants and what have you. They need to specify the behavior, the functionality, the performance and the structure. Both type of models, of course, will always be able to give you some forecasts, predictions. Predictive models forecast future outcomes given particular decisions or actions. Mainly in the support of descriptive models, in systems engineering, prescriptive models, of course, we need that. Will the system be able to satisfy the stakeholders' requirements? Next, please, Rudolf. Now, here's the problem domain. And it starts with a bunch of stakeholders who all have different mental models of what's happening, of the symptoms, what those systems mean, and of the root problem that is in fact implied by those symptoms. And then there are a bunch of people like systems engineers who try to elicit those requirements from these various stakeholders. They in turn will elicit different semantic interpretation. What did that stakeholder mean when he said that? And also mental models of what the root problem is. There's some confusion and various versions floating around.
Next one, please. So we go to the solution domain. And there's some system engineers who, given the root problem, come up with a mental model of the most appropriate solution. Those then need to be translated into detailed models, but there may be different semantic interpretations of what they were thinking about as most appropriate model. Then we get system models and system specifications. And then we're on our way, after we've verified that, validated that, we're on our way to system development. The point I'm showing is there's a lot of confusion, a lot of misunderstanding. That is why we need to standardize terminology and agree on a formal system engineering process, else we're going to end up with chaos. And that's where the issue of better models comes in. Previously, we used document-centric models, but as you can imagine, that's not very useful. What we did, systems engineering started looking at UML, the Unified Modeling Language. UML has a series of 13 different diagrams, which are pretty useful. They're very useful for understanding and communicating what you are intending to do. If you can go to the next slide, please. Here is an example of such a one. It's called a use case diagram. Now, a use case is a set of functionality that a stakeholder would use interacting with the system so that he gets measurable value from the system, because that's the beginning of stakeholder satisfaction. Here you see a microwave oven. There's a rectangle about that, which is the boundary. We have the user on the left-hand side. He has access to use case number 1, cook food, manual mode. Cook food, automatic mode. Defrost food, obtain date and time, etc. And we have a technician who also has access to all of them, and a workshop manager who's got access to repair the microwave oven. This itself shows you the type of interactions that the user will have. What we now need to do is take each of these use cases and analyze that in much more detail. Next one, please, Rudolf. And here we have a so-called activity diagram. On the left-hand, right at the top, you will see user. And this is the swim lane of the user. And on the right-hand side, you see the oven, the swim lane of the oven. And here is the first function of the first use case, 1.1. Display shows ready message. That's what the oven does. Then, and it waits. If a user now pitches, he opens the oven door, function 1.2. And immediately the microwave oven light switches on. Place food on the turntable. Close the oven door. Light switches off. Press the cooking duration button on the keypad, and the display shows enter cooking duration. Enter desired cooking duration, etc. What you can see, an activity diagram is very useful to take a use case, which is pretty broad, and break that up in all the functions that need to be performed to achieve that use case. There's a very good logic. We can check the logic in modern models to see if it's logical. Of course, each of these functions now need performance requirements defined. Next one, please, Rudolf. Here is another model, a state machine diagram. I'm sorry, I can't show you. At the top left hand, you see door. This is the door, and the door has two states: door opened, door closed. We start this bullet, dark bullet, starts with door closed. When we enter into that state, the entry is door is set to 1. That's just an indicator. And do switch on the light. If the door switch is opened, that arrow between the two, that's a guard condition. If that occurs, then the system automatically, or the door rather, automatically goes to opened, which sets the door indicator to 0. The light switches on, do the light, do display, door open message. Right at the bottom, you see the magnetron, also only 2 states. Magnetron not radiating, magnetron radiating. If we start magnetron not radiating, in other words, do this function all the time, magnetron not radiating. If food equals 1, the guard condition, which means there's food on the turntable. If the door is 1, which means it's closed. And if the timer is also 1, it means the timer had been set. We automatically go to magnetron radiating. As we enter that, the light goes on, and we do magnetron radiating, and we do turntable rotating. It shows you many, many functions linked to the dynamic behavior of the system. State machine diagram. It has a lot of detail. I've just shown you a superficial view. Next, please, Rudolf. Now, the problem is this. I've got a state machine diagram. I make a small change to one of the functions there or one of the events. Question, does that propagate to those other diagrams? And the answer is, if it's document-centric, no, of course not. And that's the problem with just having those diagrams. What we need those diagrams to be are merely different views on an integrated computer-based model. And they're just views, they're not the model itself. And that, of course, is the intent of model-based systems engineering, to create that model and to update it and etc. Next, please. One of the first things we need to do with a model is to create a meta model. And here you see the Vitek, which is a vendor who develops and provides model-based systems engineering software tools. This is their meta model. And you can see in the top left-hand corner in green, in yellow rather, use case. The use case elicits horizontal requirement in blue. It also, that curved arrow there is elaborated by a function in yellow. The function can be decomposed by further functions. The function in turn, this second to the requirement, it is based on, specified by the requirement. And a use case describes a component. It shows you all the language and all the entities that can exist. In the old ways, this was called an entity relationship model, and it's exactly that. It's called a class diagram in UML and SysML. And of course, this has now taken a long time, has received widespread acceptance in the engineering community, that we need a model, a meta model, and this is the one. Next one, please. Here you see the same model. You see there's a red dashed line in the middle. On the right, we see that model we saw a minute ago. This has now been extended to what's called operational architecture domain. In other words, this is the stakeholder domain, and what the stakeholders have and what they do and how that interfaces with the system meta model. Just an elaboration, and this is also extremely useful. Next, please. And that leads us to the definition of MBSE, model-based systems engineering. Model-based systems engineering is the application of modeling to support system requirements, formalized application of modeling to support system requirements, system design, system analysis, system verification, validation, starting in the concept exploration stage, continuing throughout development, production, and later lifecycle stages. Thank you, Rudolf. Next one, please. That's MBSE, and that's really what's happening in systems engineering now. Here is an expansion of that. It's called a model-based engineering manifesto. These guys also read the Agile Manifesto. This is taking what we're doing with model-based systems engineering to become model-based engineering. This was created in 2018. It has been presented at numerous conferences, amongst others the System Dynamics International Conference, and everybody is pretty happy with this. The purpose in orange, to motivate the transformation to model-based engineering. Below this, forced with increasing system complexity, interdependencies, breakdown of document-based methods, and other challenges, MBE, model-based engineering, provides the transformation in which we value information over artifacts, integration over independence, expressiveness with rigor over flexibility, model usage over model creation. Similar to the Agile Manifesto, and this has been accepted by a wide variety of engineering fraternities. Next, please. A comment about architecture, because that's becoming a very key topic. This is what Frank Lloyd Wright said, one of the most famous architects alive, 1977. Architecture is the science of structure, how components relate to one another, whether it is in music, painting, literature, buildings, or statesmanship. It's how components relate to one another. Next, please. So here we have the model of a system we saw before, and this is exactly what we see. We have a system of interest with a boundary. There are in 1, 2, and 3 the elements. The interfaces between the elements are there. The interconnections are there, as well as the interconnection to an external system A with external interface number 3. So this picture really represents one version of architecture. Next, please. Architecture concerns the fundamental concepts and properties of a system in its environment. And it is embodied in elements. And those elements have relationships to one another and to its environment. And also the principles guiding system design and evolution. If a system doesn't evolve, it's useless. If a system is useless, it doesn't evolve. So evolution is key, and that is a prominent feature of designing the architecture of a system. Next, please. So to summarize what I've been talking about, systems engineering and system dynamics are both based on system thinking and system principles. However, their objectives are quite different. System dynamics and system engineering. That's objectives are very different. System dynamics uses primarily descriptive models, but systems engineering uses prescriptive models. And then the last one, the next one, please. Given those differences, both can nevertheless learn a lot from each other. There's a lot to learn mutually about systems and system thinkings and how to get systems development going. I would like to close off with a long quote, and I'm sure you've discussed this type of thing before, but let me add my contribution. Quote, all scientific models have restricted applicability. None of them is the truth. Scientific models are representations of reality, not reality itself. No matter how well a particular model works, it should always be regarded as an approximation and important as an aid to the imagination rather than as the ultimate truth. Next, please. For instance, is light a wave or is light a particle? This set physics ablaze at the turn of the last century, 1900s, and still it causes problems. The proper answer is that under certain circumstances, light behaves as if it were a particle, a photon. But under different circumstances, light behaves as if it were a wave. The better scientist takes the as if for granted, but the lesser scientists, guys like you and me, often forget this crucial as if distinction. Next, please. There is no paradox or conflict here. The limitation lies in our model and in our human imagination. We are trying to describe something that is light, that is in its entirety, unlike anything we have ever experienced with our own senses. Richard Feynman called it the result of an uncontrolled but vain desire to see light in terms of, next please, in terms of, I forget the quote, it'll be there in a minute. Something familiar. The model of light doesn't have to make sense in our normal everyday terms. Quote by John Gribben in a book of his. And that's rather important. To summarize that, next please, Rudolph. So under certain circumstances, M, the model, behaves as if it were the system. But that is not equal to saying M is the system. That's a fundamental problem, and the guy who summarized that best was René Magritte, a Belgian surrealist painter who painted a pipe. And the name is Ceci n'est pas une pipe, meaning this is not a pipe. Everybody thinks that's a pipe. This is merely a graphic representation, a view on that pipe. And that's about all I wanted to say. How is my time doing?
You're spot on for timing, Pat.
These are two ending. Can I make these two ending
Yes, please.
comments?
Yes, please.
One of the problems, or two of the problems of systems engineering is the following. Vusi is an expert on toasters. He's maintained them for very long. He uses them every morning when he puts bread in there to toast that. And he's been designing them for many, many years. He is an expert on toasters. Now, as you know, all systems live in a hierarchy. Now keep it there. Live in a hierarchy from lower levels to higher levels to still higher levels. One of the principles of that hierarchy, keep it there if you can, is that the principles at one layer in the hierarchy are identical to the principles in another layer of that hierarchy. Now this leads some people to say, if we've got a system engineer who's a master at toaster, by the principle of a hierarchy, he will also be a master on the economy, because that's also a system model. Hence, let's give him to operate and advise us on the economy. And that, of course, is plain nonsense. The objectives of a toaster are trivial. The economy is a dynamic political balance between many conflicting objectives of different groups of stakeholders. Is the economy a model to give us full employment? Is it to create maximum growth? Is it to create a circular economy? Is it to be something that we can steal from? Is it to be, and there are lots of different objectives. So that's a danger. People think if they can jump layers in the hierarchy, and that's nonsense. And then the politicians. And in the United States in the late 80s, or late 60s rather, and the 70s, they were saying, we placed a man on the moon. That took a lot of talent, of complex things. We also have inner cities in our big cities. The inner cities are essentially ghettos. We've got all this talent in systems engineering. Why don't we get them to solve the socio-economic problems of the ghettos for us? And that's the metaphor, and it is equal dangerous nonsense. Those are some of the dangers of people using systems engineers. Thank you very much. If there are any questions, and if we've got the time, please.
Thank you very much. That was a very interesting overview of what systems engineering is and how it does link to us as systems dynamicists. Could I ask if we've got time for one quick question? Is there anybody who wants to ask a question? Rudolph, you prepared one, I think.
Yeah, I have many, but I think the elephant in the room. So where would you say is can you apply system dynamics as part of your system engineering process?
It is often used in those early stages where we want to define what the root problem is and exactly what the nature of that problem is. And for that purpose, you can often use system dynamics to determine whether it's dynamic, what the time constants are, but to help you with the stakeholders finding out what exactly is happening. That's one of the classic applications of systems dynamic in systems engineering. So we use the standard causal loop diagrams, stocks and flow diagrams, feedback in problem identification and defining the root problem.
Yes, and I would also say, okay, this might not be really system engineering, but if I talk to system lifecycle, even during operation of the system, when you have to make policy decisions on what strategy to follow for maintenance, etc. I think in there it can also be applied, I would say.
Well, I hope that all of those logistics issues have been sorted out during development, but it's for sure if we place the system in its environment, of course it influences the environment and in turn is influenced by the environment, and that we might need to model later on during the life cycle and identify problems which weren't picked up originally. So absolutely, we can learn a lot from each other.
Okay, thank you, Art. Thanks, Rudolf. Yeah, I also think that when it comes to evolving systems, that is maybe a spot where system dynamics can also help. But yeah, so thank you very much, Art. We really appreciated this presentation.